Near the beginning of Lagrangian mechanics, we argued that there are few alternative formalisms of classical mechanics, namely the Newtonian mechanics, the Lagrangian mechanics, the Hamiltonian mechanics, and the Hamilton-Jacobi theory, of which we have studied Lagrangian mechanics extensively in our previous classes. Today we start our journey to Hamiltonian mechanics. As we have stated earlier that no one formalism provides any new physics. Only the fact is that one method may be helpful in solving a particular problem, and there are different approaches. One formalism may be helpful in one aspect while the other may be found to be helpful in another aspect. Mm, as we shall show afterwards that the Hamiltonian mechanics puts the classical mechanics in a form which the transition from classical to quantum or classical to statistical mechanics is very helpful through Hamiltonian mechanics. As we shall see afterwards, the equation of motion in classical mechanics, the Hamiltonian form of classical mechanics, is similar to the equation of motion in quantum mechanics, and the concept of phase space as introduced in Hamiltonian mechanics is extensively used in statistical mechanics. However, we are presenting today's lecture under the Hamiltonian heading Hamiltonian mechanics, but today we are going to discuss a, one thing, a mathematical property, that is the Legendre transformation. Legendre transformation. This Legendre transformation is used to change a variable of a function by its conjugate function, and we get a new function which has the same dimension as the previous. The Legendre transformation has extensively been used in thermodynamics, and another biggest user of Legendre transformation is obviously the Hamiltonian mechanics, which the Hamiltonian itself utilizes this theory, and the canonical transformations uses this Legendre transformation extensively. Let us consider a function x, f, which is a function of x and y. We have a function f of x, y. So we calculate df is equal to del f del x dx plus del f del y dy. We alternatively write it as u dx plus v dy, where u is del f del x and v is del f del y. We consider a function f1 which is a function of this sort, x del f del x. So it is f minus xu. So df1 is equal to df minus x du plus u dx. As we write the expression of df, it is u dx plus v dy minus x du plus u dx. The u dx term cancels and we get minus x du plus v dy, which shows that f1 is a function of u and y. you note that the coordinate u, the variable u is obtained from from f through partial derivatives with respect to x. So x and u are conjugate variables. So obtain a new function in f1, a new function f1, which is obtained from f by replacing x by its conjugate variable u. One thing, if we consider function f1, y is both, they are both in f and f1, so y is called a passive variable which do not undergo any change, and x and u are active variable because x of f is being replaced by u in f1. So x and u are, in this example, f as the passage from f to f1, x and u are active variable and y is passive variable. And furthermore, one thing, we may differentiate it from this relation. We get del f del u is equal to minus x, del f1 del u and del f1 del y is equal to v. So v is obtained for passive variable. It is the v is the partial derivative. V is the partial derivative of f with respect to y. It is also the partial derivative of f1 with respect to y. So this is the relation of passive variable which does not undergo any change. But this is the transformation involving the active variables. Note a change in sign. Here there is a negative sign, here there is no negative sign. The fact will be clear if we consider one more transformation. We consider f2 as equal to f minus yv. Or one more thing, f and f1 has the same dimension. So the Legendre transformation, this is the Legendre transformation. This transformation creates a new function f1 from the old function f by replacing one or more variable by the corresponding conjugate variables. Here we consider this function, then df2 is equal to df u dx plus v dy for df minus y dv plus v dy. So this is u dx minus y dv. So this shows that f2 is a function of x and v. And let us calculate del f2 del x is equal to u and del f2 del v is equal to minus y. You see that u, here x is the passive variable, so u is same. The u is the partial derivative of f with respect to x. It is also the partial derivative of f2 with respect to x, and there is a change in sign. Another transformation relation is that f3 is considered as f minus xu minus yv. So this is f3 is equal to u dx plus v dy for df, then minus x du plus u dx for this term, and then minus y dv plus v dy from this term. U dx cancels with this, v dy cancels with this. So we have minus x du minus y dv. Here you see that in this f1 y was passive variable, in f2 x was passive variable, and in f3 there is no passive variable. So del f3 del u is equal to minus x, and del f3 del v is equal to minus y. You see that when we replace one variable, few variables, but not all, then there are active and passive variables. The active, there is a change in sign between active and passive variable in the transform function. The sign may appear with opposite sign, because sometimes one uses this transformation as x du minus f. This is the convention that we have used over here, is the convention that we are generally accustomed to use in thermodynamics, and in classical mechanics the reverse definition will be used. So this is the definition that we use in thermodynamics, and in classical mechanics we shall use an alternative form, that is x u minus f. This definition will be used in classical mechanics, in which case there will be a reversal of sign. We shall explain this Legendre transformation for thermodynamic functions. If we consider the combination of first law and second law of thermodynamics for a reversible, infinitesimal reversible process, for as applied to an hydrostatic system. So, for an infinitesimal, for a hydrostatic system, the first and second law of thermodynamics is TdS is equal to du plus PdV, or du is equal to TdS minus PdV. That is, we consider U, internal energy U, as a function of entropy and volume. One thing, that conjugate variable to S is obtained, del U del S is equal to T. So T is the conjugate variable of entropy, and the conjugate variable of V is del U del V is equal to minus P. So minus P is the variable conjugate to V. Now we consider a function which is obtained from U by replacing S by its conjugate variable. So we define del U del S. So this function is U minus TS. We know that this function is known as Helmholtz free energy. Helmholtz free energy, F. And if you take the differential of F, we find that it is du minus TdS minus S dt, and for du we write TdS minus PdV minus TdS minus S dt. So TDS goes. So this is so this is minus SDT minus PdV, which shows that Helmholtz free energy is a function of T and V. This is what we intended for. We tried to replace S of U, S in U by its conjugate variable. So we get another function F having the same dimension of U. And we can find out that del F del T is minus S and del F del V is minus P. So we get del F del T is equal to minus S and del F del V is equal to minus P. You note the change in variable. This is a variable change, and since in this case V is the passive variable, this relation is same. The relation with respect to V is same. So this is the nature of passive variable. Now we consider another function. We replace V in U by its corresponding variable. So we replace U minus V del U del V. So this is U plus PV, because del U del V is minus P, del U del V is minus P, and we know this is the enthalpy function. So dH is equal to du. For du we write TdS minus PdV. For du PdV plus VdP. So this is TdS plus VdP, which shows that H is indeed a function of S and P. Here V has been replaced by its conjugate variable P, and furthermore we see that del H del S is equal to T, and del H del P is equal to V. You see that S is the passive variable. S is the passive variable, so this is the relation of passive variable, and the active variable, there is a change in sign. And finally, we want to change both T and S and V of U. So we need to replace U by S minus del U del S U minus S del U del S minus V del U del V. So this is U, this is minus Ts, because del U del S is T, and this is PV, because del U del V is minus P, and this is, we know that this is Gibbs free energy. This is enthalpy. This is enthalpy. So if you take the differential of dg, then this is from S, it is TdS minus TdV. This is from du minus TdS plus SDT plus PdV plus VdP. TdS cancels. PdV cancels with PdV. So we have minus SDT plus VdP. So G is indeed a function of T and P. Furthermore, del G del T is equal to minus S, and del G del P is equal to minus V. Note the change in sign for in both the relations. Sorry, this is plus. So these are the Legendre transformation that we have used extensively in thermodynamics. Now we return back to the general theory of Legendre transformation. So we consider a function of n variables. F is a function of n variable x1, x2, x3, etc. Up to xn. So general theory, we have a function f is a function of x1, x2 up to xn. And if we write df is equal to, we get summation over I is equal to 1 to n del f del xi dxi, which we write summation over I is equal to 1 to n ui dxi. Here we have written ui is equal to del f del xi. Now we want to replace the all the x in f by the corresponding conjugate variable. To do this, we define g as a function of this f minus xi del f del xi, so that this becomes f minus del f del xi is ui, so summation xi ui. Then we take dg is equal to df minus summation over I is equal to 1 to n xi dui plus ui dxi, and for df we write this one ui dxi minus summation over I xi dui plus dui dxi. So ui dxi goes, so we get minus summation over I is equal to 1 to n xi dui, which shows that g is indeed a function of ey's u1, u2 up to un, which we write as so. In making a transformation from f to u, we have replaced all the independent variables x1, x2, xn by the corresponding conjugate variables, and the relation that exists here is xi is equal to minus del g del ui. So these are known as the dual transformation. Dual transformation means this transformation allows us to know f function, and these are the partial derivatives of f. When we switch over to g, which is obtained by replacing x's by their conjugate variable, then the partial derivatives of g are given by this. So these relations are known as dual transformation. In this transformation, all the x's are considered to be active variable because all the x of f have been replaced by the corresponding u's in g. There may arise a situation when one do not want to change all the variables. Actually, when we switch over from Lagrangian to Hamiltonian, we replace all the velocities by their conjugate variable momenta. So when we change all the variables, we use such a transformation, and sometimes it is found to replace only a few, not all the variables. Then one uses the transformation which changes only a few variables of the original function, not the all. These are all the Legendre transformation involving passive variables. We consider a function f which is a function of x1, x2 up to xn, and then y1, y2, ym. And obviously we know that df is equal to summation over I is equal to 1 to n del f del xi dxi plus summation over j is equal to 1 to m del f del yj dyj. We write it as summation over I is equal to 1 to n ui dxi plus summation over j is equal to 1 to m vi vj dyj, where we define ui is equal to del f del xi and vj is equal to del f del yj. We first want to replace the x in f. So if we want to replace xi by the corresponding ui, what shall I do? We define g is equal to f minus summation over I is equal to 1 to n, the number of xi del f del xi. So this is f minus summation over I is equal to 1 to n xi ui. So we calculate g dg. dg is equal to df, and for df we write so this is for dg, it is df minus summation over I is equal to 1 to n xi dei plus ui dxi. And for df we write this expression, so we see that this part goes, so this part minus this part survives, so we have minus summation over I is equal to 1 to n xi ui plus summation over j is equal to 1 to n vj yj, which indeed shows that g is a function of ui and yj. So here yj are passive. Here yj, these are passive variables which does not undergo any change as we make a transformation from f to g. And one more thing, that del g del f del g del ui del g del ui is equal to minus xi, and del g del yj is equal to vj. You see that vj is the same definition in both, because vay is passive variable and the active variable is this. There is a dual transformation and we know the change in sign. We consider another transformation in which we replace yj by vj. What shall I do? So we define h as equal to f minus summation over j is equal to 1 to m we want to replace yj, so del f del yj, so this is f minus summation over j is equal to 1 to m yj vj, and we calculate dh is equal to df, so this is df is equal to summation over I is equal to n ey dxi plus summation over j is equal to 1 to m vj yj, and if we take the differential this summation over j is equal to 1 to m, this is yj vj plus vj dyj, and this cancels, this minus and plus sign cancels, and we get summation over I is equal to 1 to n ey dxi minus summation over j is equal to 1 to m yj pvj, where we see that h is a function of xi vj as we intended for, and we may get that del h del xi is equal to ey, and del h del vj is equal to minus yj. We compare this, since x is independent passive variable, same transformation relation, and this active variable, this dual transformation, and there is a change of sign. Active variables will have a particular sign. In transform function, active variable will have a certain sign, and the passive variable will have the opposite sign. Similarly, we may define another function k as f minus summation over I del f del xi minus yj del f del yj. If we write it in this form, then Einstein summation convention is used. That is, there is a repeated index, so summation over I is implied over all possible variable values, so I is equal to 1 to n, and there is summation over j is implied over j is equal to 1 to m, and on explicit calculation we see that this is minus xi dui minus yj dvj. So we says that the function k is a function of ui vj. So there is no active variable. Sorry, no passive variable here. In this case, x is passive, xi is passive, and here there is no passive variables. So these are the Legendre transformation. So basic thing that we have to keep in mind, that by Legendre transformation we may change one or more function variables of a function by the corresponding variable, corresponding conjugate variables. The function, the quantities or the variables which undergo no change in the original function and in the transform function is known as the passive variables. And the active variables are replaced by their conjugate variables, and the original function and the transform function have the same dimension. That is the main objective of Legendre transformation. We shall just mention what we will do in classical mechanics or in Hamiltonian mechanics. In Hamiltonian mechanics, one starts with the Lagrangian and then lands up with the Hamiltonian. The Lagrangian L is a function of qi dots and t. This is the coordinates, velocity and time. And we come to Hamiltonian, which is a function of qi, pi and t. So these q's, they are interchangeable. That is, we know that del L del qi dot is equal to pi. So the velocities, generalized velocities of Lagrangian is replaced by the conjugate variables, that is the momenta, generalized momenta in Hamiltonian. And you see that Q and T are there in both H and L. So Q's, the set of Q's and T's are the passive variables. And we shall show that they will have the same relation, sort of relation. That is, we have, and another function which we shall produce is the Roth function. Roth function is obtained from Lagrangian by replacing few of the q's, that is qi's. So all qi's there. Say we replace, this is pi, p1, p2 up to pk. So pk, they are being replaced, and then qk plus qk dot k plus 1 up to qn dots are there, and t, in which case we replace only only few of the velocities by their corresponding conjugate variables. And so the q's and t's are there both in R and L, they are passive variables, and these sets, that is q dots from k plus 1 to q dot, and they are also passive variables. In fact, as we shall show afterwards, that Rothian is an hybridization of Lagrangian and Hamiltonian dynamics. So with this introduction to Legendre transformation, we shall start the Hamiltonian mechanics proper in the next lecture.